Hello everyone, this is the WCRP CMIP6 analysis poster session. We're holding these online poster sessions as a sort of forum for discussion of CMIP6 results. And we're aiming, this is the April session. We've had 4 slots. This is the final one for April. And we're hoping to hold another poster session online in May, and we've still to decide on the dates for that. In this session, just for those who've not attended before, there'll be 5 short presentations, somewhere between 8 and 10 minutes, followed by a few minutes questions and answers at the end of each presentation. I'll be moderating the chair. My name's Andrew Yule. I'm in National Oceanography Centre in Southampton. Well, I'm actually not there, of course, but that's where I'm supposed to be. If you want to raise a question or make a comment, please use the chat facility in the Zoom session. We might not have time to answer all the questions or to raise all the questions, but we will capture them in the Google Docs that were sent out in the invitation. And you're welcome to add these to these documents as they just to further discussion. We're recording the poster sessions and we aim to put them out on the UKSM website, and we'll be sending details about that to all participants. If I could ask you to keep your microphones muted throughout, and it's probably not a bad idea as well to turn off the video just to reduce bandwidth issues that we may have. So with that kind of out of the way, I just want to introduce the first speaker is Jon Seddon from the Met Office, and he's going to be talking about HighResMIP. So John, take it away, please.
Hi, my name's Jon Seddon from the Met Office, and my brief talk today is in 2 parts: a quick overview of the PRIMAVERA project and what data we can provide to you and what tools we had to develop to allow PRIMAVERA project to work. And then second part, a Python tool we've developed which might help you analyse CMIP6 data. So the PRIMAVERA project is led by the Met Office. It's an EU Horizon 2020 funded project. And the part of this I'm involved with is a set of coupled and AMIP simulations at standard and high resolution. And so the historic runs from 1950 to 2014, and the future from 2015 out to 2050. And in PRIMAVERA, we've got 7 different climate models from around Europe running these simulations at standard and high resolution. Standard is standard CMIP6 resolution, and high is typically 25 kilometers in the atmosphere. Because we've got these massive high resolution simulations in PRIMAVERA, the 7 models are due to develop almost 2 petabytes of data, and so we've had to develop quite a strong data management plan to be able to cope with this data. On the right hand side here, you can see the flowchart we developed in the data management plan. So we've got 7 different climate models running on HPCs across Europe who are generating the data. They transfer these to a group workspace at Jasmine, where immediately we validate the data. So we check the metadata is correct, the files are in the correct format. Then also we strip out the metadata and store it in the PRIMAVERA database. The data is then moved from group workspace directly to tape, and the data is deleted from group workspace to free up disk space for more data to be uploaded. When users are then connected to the database, we've got the data management tool, or DMT. Part of the DMT consists of a web interface to allow users to query what data we have available. So when users want to analyse the data, they can go to DMT, see if the variables they need are there and for which models have produced them. And then they can, if the data is available, and it gives them the address of the data. So the data is on group workspace, they can analyse it. If the data is only currently available on tape, they can use the DMT to request that it's restored from tape to group workspace, and they're sent an email, typically within sort of 2 hours or a couple of hours, possibly a couple of days, when the data is available to them on group workspace. And actually, to make most efficient use of group
I think we lost you there, John.
Workspace in Jasmine set of.
Sorry, John.
Say again, sorry.
We seem to be losing you, John. Do you want to try and repeat that last sentence or 2?
Okay, yeah. So when users want to to make best use of disk space, then users restore a small subset of data, develop their analysis on the interactive data analysis servers, and then when they want to run the full analysis, they can restore the full set of data from tape to group workspace, run their analysis on the Lotus batch cluster at Jasmine. When they're happy with their results, they can use the DMT to mark the data as complete. And if no other users are still analysing that variable, it can then be deleted to free up space for more data. So for most of the project, we've had the data only available to Primavera users at Jasmine, but now we're coming to the end of the project. And so we're now submitting it to ESGF, and actually we're submitting it to the HighResMIP component of the SGF of CMIP6, and HighResMIP is actually led by some of the Primavera project members. Because the data is now available in ESGF, it's also available in the CEDAR archives, and so it's available to all users at Jasmine under /BADC/CMIP6 at Jasmine.
John, I think we might have lost you again. Can you hear us?
Yeah, I'm connected again. Can you hear me now?
Yes, we can, thanks.
Okay, sorry. Okay, here we have a screenshot showing the data management tools web interface. So here someone's querying the RSUT variable, which is the top of atmosphere outgoing shortwave flux for HighRes Future, which is the coupled future experiment. So here you can see that some data, and you can see the first few models to produce this variable. So some have an online status of online, meaning that all of the data is available on group workspace. Some is partial, so some is available on tape, and some is available on group workspace, and some of it is offline. Users can click in the right-hand column to request that data that's not online is restored from tape to group workspace. So we found that the combination of Jasmine and the data management tool has been very effective in allowing 100 users from across Europe to work on this multi-model dataset. We'd really recommend that future projects working with multi-model, multi-institute datasets use facilities such as Jasmine. And we've made the DMT available, freely available, and open sourced it. It is customized for Primavera at the moment, and would require some work for projects to use. That's available for users to use. We'd really recommend that combination. So just changing that to next slide. Sorry, it's going a bit slowly here. Hazel, could you change to the next slide, please? Fantastic, thank you. So for the last year, I've had an industrial placement student called James Bedwell working with me, and he's developed the Cube Helper module. And it's primarily, it's very useful to allow users working with the Iris Python library to work with CMIP5 and CMIP6 data. Iris struggles with CMIP data because of typically one variable is split across multiple files. And there's metadata differences in each file, such as the history attribute and the unique ID attribute, which means that Iris is unable to concatenate them into a single cube.
2 minutes.
Many users code to enable this to take place. This is quite inefficient, as slightly different functionalities required every time. So Cube Helper is a Python module that acts as a wrapper for many common Iris functions. So it identifies inconsistencies, removes them, warns users what it's done, and then returns a single cube. It's installed for all users at the Met Office, and we also made it freely available, and you can see it just there for GitHub for users outside of the Met Office. Can I have the next slide, please? So here you can see an example of working with CMIP6 data. So on the left-hand side, we've got Iris, and there's 7 different lines of code you need to return a single cube. And these lines can vary from variable to variable. With Cube Helper, it's much easier. So it's import Cube Helper as ch, then cube equals ch.load and path to data. And then it will look at the data, identify any inconsistencies, remove those metadata inconsistencies, tell you what it's done, and then return you a single cube that you can then work with. If you've got any questions, then please contact James or myself, address there, or raise an issue in GitHub. Thanks. If anyone has any questions.
Thanks very much, John. Thanks for that. sorry about the technical problems we're having. A couple of questions for you, still got some time. First one comes from Jeremy Walton, the Met Office, and he's asking how much work would it take to make the DMT less Primavera specific?
I'm not totally sure at the moment, I'm afraid, and we do have plans to use it in other projects. So after the end of Primavera in July, then that's one of the things I'll be looking at and hopefully applying it to some other problems that we've identified.
Okay, another one from Pat Hyder, just asking how Cube helped work. How does Cube help work for ocean data and the irregular grids? How does it work for the irregular data, like for instance from Orca?
Yeah, it's just Cube Helper is only working with metadata, and so it works with any CMIP6 data, and it just removes metadata inconsistencies. So it can't tell the difference and doesn't care about the difference between atmosphere and ocean data. So it works perfectly well with Orca grids. Okay,
I think we've got a couple of other questions there, but we'll capture those for later, and we'll move on to the next talk if that's kind of all right. So next up we have Catherine Hardacre, again from the Met Office, and she's going to talk to us about sulfate and sulfate observational data to evaluate the aerosol sulfur cycle in UKSM1. You there, Catherine?
I'm here, yep, can you hear me?
Yes, we can. Take it away.
Okay. Hazel, could you move on to the first slide, please? Thank you. So thanks for tuning in. I'm going to speak about the evaluation of SO2 and SO4 in UKSM1. And just a quick thanks to Jane Mulcahy, Steve Rumbold, Colin Johnson and Colin Jones, who have all had input to this work. So the reason we're interested in SO2 is because it's emitted to the atmosphere from a number of anthropogenic and natural sources, and once in the atmosphere, it oxidizes to sulfate aerosol, which has an important role to play in acid deposition, atmospheric aerosol loading, and in cloud properties, and therefore it's important for the Earth's radiation balance. So it's important for models to represent this process well, so you can predict future climate. Okay, so there's a couple of reasons why we're interested in looking at evaluating SO2 and SO4 in UKSM1. So firstly, SO2's been decreasing globally since about the 1980s, and you can see the global trend in the decrease in SO2 emissions in this bar chart in the left-hand plot here, which goes from 1990 to 2015. However, that decrease is not uniform across all regions. So if we look at the bottom two time series here, you can see that legislation has driven decreases in SO2 emission from Europe and North America. If we look at this top time series here, we can see the emissions are still increasing in East Asia. And the models need to be able to capture these trends so that we can have confidence in our future predictions. The second motivation for the work is that we've recently done some development of UKSM1 to correct for this cold bias in global mean surface air temperature. So you can see here in this time series that where UKSM is in the blue and the observations are in purple and black, that the model is too cold for much of the early 20th century. And this issue was attributed to too much sulfate, not solely, but partly attributed to too much sulfate aerosol in the atmosphere. So a certain amount of development work has been done to modify the sulfur aerosol precursors and processes in the model, which I'll come to in a bit. Okay, so in this series of plots here, we're comparing UKSM prior to including the bug fixes and modifications to sulfur aerosol processes. And we're comparing it against observations for surface SO2 concentration, surface sulfate concentration, and SO2 dry deposition. The reason we're interested in the dry deposition process is because some of the modifications we make to the model are relevant to that process, and I'll talk a bit more about them on the next slide. So the observation networks that we're comparing against are based in the US, so that's the CASNet network, and I've divided those sites into the western sites, which are less polluted, and the eastern sites, which are more polluted. And then we have the EMAP network, which is based across Europe. You can see the sites here in the bottom right-hand map. We don't have dry deposition observations from the EMIP sites. So in each of the plots, we take the mean, the annual mean from 1987 to 2014, and we take the mean across all of the sites, and then the bars and the shaded regions represent the standard deviation across the sites. And we've got the observations in black and the model is in blue. So the first thing to note here is that the model does capture the trends very nicely across this period. So you can see that the model captures the decreasing concentrations and deposition. However, the model does have a number of biases. So for SO2 concentration, you can see that the model is biased high across all of the regions. The sulfate concentration, which is the middle row here, the model is biased low in the polluted regions, but slightly high in the cleaner region of the Western USA. And we can see for, oh, sorry, we'll just go back and finish off what I was saying on that slide. Okay, and for SO2 dry deposition, you can see that there's also a positive bias, which was likely being driven by the positive biases in SO2 concentration. Okay. Okay, so these series of plots are the same as the previous panels, but we have the addition of UKSM1 with the bug fixes and modifications, which are shown in the red lines for all of the plots. Okay, so the bug fixes and modifications that have been implemented, a lot of them are focused on the dry deposition process to improve the treatment of this process in the model and to increase the dry deposition and therefore remove SO2 from the atmosphere. And sorry, I'm not moving the mouse, it's moving by itself. So they're acting to remove SO2 from the atmosphere and reduce the amount of SO2 that is available for conversion to sulfate. So again, we can see from the, thank you, the top row of plots here that the bias in SO2 concentration is reduced by these fixes and modifications. And if we look at the global mean surface air temperature, where the modified model is in red, we can see that the temperature bias is also improved. However, we do, by removing more SO2 from the atmosphere, we reduce the amount available for conversion to sulfate, and it is increasing our negative bias in the polluted regions. And of course, by increasing our dry deposition with these modifications, we increase our positive bias in SO2 dry deposition. So our next steps are to do a more detailed evaluation. We have the problem that SO2 is generally emitted from point sources and has a relatively short lifetime of about 2 days. So about half of it is dry deposited and oxidized quite close to the source. But we're, of course, comparing with the model, which is on the grid box scale. And of course, our observation points are also at a point rather than the grid box scale. So we will identify some observation sites that are close to sources and try and understand the model's behaviour better in these regions, in these areas close, in the grid boxes, sorry, close to the source regions. Okay, thanks.
Thank you very much, Catherine. We've got one question so far. If anyone wants to put any more, more appearing, okay, good. So the first question comes from Jeremy, and he's asking that the SO2 and SO4 were decreasing in Europe and America, but not in Asia. And he was asking if there's been a comparable comparison between UKSM and observations from that part of the world.
I need to check if there's anything published. There is in a data set called East Asia Net, which has sulfate concentrations for East Asia that we do have access to. I haven't included any analysis of that here. Steve Turnock leads has had a look at that, however. The downside of that is it doesn't have the corresponding SO2 and SO2 concentrations and dry depositions for us to look at, so we can do more of a complete analysis.
Okay, Dave Stevenson's asking if the, he suggests, doesn't it look like SO2 to SO4 conversion is too slow?
Yes, that might also be a problem. We hope to have a closer look at the oxidation processes in UKSM as well. That might be the next lot of work I've got on my plate.
Okay, and we've got a bit of time, so I'll just ask one final question. This is from Richard Wood. He's noticing the biases are reduced but not eliminated. And if we fix the biases altogether, would we expect the GMST to be too warm throughout the 20th century?
I couldn't say. I mean, the problems with the dry deposition, or the modifications that we've made to the dry deposition, are not the only reason for the cold bias, and there are other developments that are going into the next version of UKSM1, which will have different effects and impacts. You can see from the red line on that plot of global mean surface air temperature that we are now overshooting a little bit towards the end of the time series. Yeah, there are more developments within the model to be made than just the SO2 dry deposition modifications. Sorry, that's a really waffly answer.
That's fine. Thanks very much, Catherine. So we can move to our next talk, please. That's from Jonah Bloch-Johnson from the University of Reading, although I'm not sure if he's actually there. And this is climate sensitivity under higher CO2 due to positive feedback temperature dependence. Jonah, are you ready?
Yes. Can you hear me?
Yes, we can. Thanks.
Okay, wonderful. Let me just see. Just want to see if I have the screen. I do. Wonderful. So I'm Jonah Bloch-Johnson. I'm a postdoc at the University of Reading, and I'm here to talk about how climate sensitivity increases under higher CO2 levels due to positive feedback temperature dependence. This is very much a collaborative work. I want to thank my collaborators, Maria, Martin, Tim, you, and Jonathan. I also just want to thank the organizers and for all of you for being here in these unusual circumstances. By climate sensitivity, I specifically mean the equilibrium global mean surface warming per CO2 doubling. And the simplest way to estimate the climate sensitivity would just be to take a climate model, spin it up under pre-industrial conditions, and then to double the CO2 concentration and let it come into equilibrium at the new level. The issue with this, of course, is that it takes a long time for this equilibration to occur. And so typically models only run for about 150 years, and then the remaining warming is estimated using a regression towards the end of the simulation. This plot shows for the colored bars that are above the 2 times, the estimates of the warming under abrupt 2 times for CMIP6 models and some models from the long-run MIP data set. Because of the the low signal-to-noise ratio for abrupt 2 times simulations, an assumption is often made that the warming per doubling is constant, so that you could instead do an abrupt 4 times simulation and then have the resulting warming to estimate how much the warming would be in response to an abrupt 2 times increase. And that, of course, is the actual default experiment used in the CMIP deck to estimate climate sensitivity. And so here, those values are shown by the 4 times divided by 2 colored bars. And you can see that for a lot of the models, these values are actually different. And in fact, we only have these abrupt 2 times estimates thanks to the non-lin MIP experiment project organized by Peter Good. And in some cases, thanks to Tim Andrews for this particular had GM3 simulation. But as you can see that the warming from the 2 times is not exactly the same as half the warming from the 4 times. This picture becomes even clearer if you include also half times CO2 experiments or 8 times CO2 experiments in the long-run MIP project. In general, you can see a trend that for most models, the higher the CO2 level, the more warming you get per doubling. This becomes even clearer also if instead of just using the first 150 years of these simulations, we use the full length of simulation available, which for the long-run MIP models is at least 1,000 years. We also have longer runs for some of the CMIP6 models, once you include the fullest possible length for all models except for this GIST model, the equilibrium warming per doubling goes up with CO2. So why might this be? The warming is proportional to the radiative forcing that causes it, and it's inversely proportional to the radiative feedback by which that warming rebalances the top of atmosphere radiative fluxes. So a first theory for why the warming might be increasing nonlinearly with CO2 doublings is that maybe the forcing is increasing nonlinearly with CO2 doublings. People typically assume that this climate feedback is a constant, at least for the equilibrium feedback. So we can first try to keep that assumption that the feedback is constant, but that it's the forcing that's driving this equilibrium nonlinearity. So this is true if the factor by which the equilibrium warming exceeds what you would expect from just linearly extrapolating from the 2x experiment, if that nonlinear factor for warming is the same as the nonlinear factor for forcing. So the factor by which the warming exceeds its 2x experiment is the same by the factor which the forcing exceeds its 2x experiment. And that's shown in this plot. So for all the models to the right of this line, they warm more than you would expect from the linear approximation. You can see that that's true for almost every simulation. There's actually two that are outliers that are out past 1.8, which is the CS2 and the famous simulations. For forcing, if all of the forcing was greater than you expect from the linear approximation, then I'll be above this line, but in fact, there's some that are below, there are some that are above. On average, the forcing is actually fairly linear. Most importantly, if the forcing explained the warming increase, then all of the dots would fall along this one-to-one line. In fact, for most of the simulations, the increase in warming is greater than the increase in forcing with CO2 doubling. So the forcing isn't sufficient to explain the increase in warming. So instead we turn to the feedback. The feedback, instead of being constant, well, we can now assume it's a function of temperature and CO2 concentration. We take a Taylor expansion of this feedback around at the pre-industrial value of the feedback, and then include these feedback temperature dependence and feedback CO2 dependent terms. We're going to assume just in this slide that the feedback CO2 dependence is negligible. If you have if you have a question about, I'm happy to talk more about that assumption, but it ends up not having a qualitative impact on our results. But the feedback temperature dependence and the pre-industrial feedback, these two terms, if we drop the feedback CO2 dependence, we can use our estimates of the forcing and the equilibrium warming to estimate these two values for each model. We have the feedback temperature dependence versus the pre-industrial feedback here. If the feedback temperature dependence is positive, you end up warming more than you would otherwise. You can see that that's the case for most of the models. And in particular, if the feedback temperature dependence is large enough for a given CO2 level, then you enter into a runaway where more warming increases your feedback more, gives you more warming, and increases your feedback more, and you get runaway warming, you lose your stable state. And these solid lines give those thresholds for 4x and 8x CO2. So even if you aren't to the right of these thresholds and aren't in a runaway for that CO2 level, you can still experience a large increase in your sensitivity at that CO2 level if you're close to that threshold. So for instance, all of the models that are to the right of this dashed line experience an additional 3 degrees of equilibrium warming under 8x CO2. So their sensitivities are, the warming per doubling is an additional, at least additional degree. And that's the case for most of the models. So we can assess how important this is for actual projections of warming by taking a Monte Carlo simulation of 2-layer models where we're using parameters for these two-layer models, but that have the same mean and covariance as the ensemble of models that I've been discussing. So in essence, we're trying to sample the uncertainty on all of the different aspects of the energy balance system in these models. And we're running these models under a high emission scenario. So it's SSP 8.5, with a scenario that plateaus at around 8 times CO2 by the year 2250. And
One minute.
Okay, we rerun this experiment with the feedbacks assumed to be linear and the forcing assumed to be linear, and then with both of those either with nonlinear or linear feedbacks and forcings. By 2100, there's almost no change to that from these nonlinearities I've been discussing in this talk. In the far future, by 2300, there is a difference, but it's all due to the nonlinearity of the feedback as opposed to the forcing. You have a 10% increase in the 50th percentile of warming, or excuse me, 13% increase. You have a 23% increase in the 80th percentile, and you have a 5% chance of runaway warming by 2300. So to summarize, for almost every model, equilibrium warming per doubling increases with CO2 level. For almost every model, the forcing is not enough to explain this increase. For almost every model, there's a positive feedback temperature dependence, which does seem to explain this increase. And this effect is not necessarily important for warming in this century, but could be important for assessing the risk of high warming in the coming centuries. Thank you very much for listening, and I'm happy to take any questions.
Thanks, Jonah. We've got a couple of questions already. Kat Senior is asking, do we understand the physical reasons for the nonlinearity in the feedbacks? And are they the same across different models?
So thank you for asking that. Oh, is it still possible to, I have an extra slide about this. It's just the first one. Is it possible to advance to it? So just as a first look, we can break down this feedback temperature dependence between different fluxes, and it seems like it's really the long wave clear sky feedback that's the most responsible. And so in particular, the water vapor feedback seems to be, gives you basically a positive feedback temperature dependence. Excuse me, the long wave clear sky feedback has a positive temperature dependent component for all models, whereas all the other terms on average it's 0. And so the spread seems to come from shortwave clouds, much like the normal feedback but for the reason that it seems to be positive for all models seems to come from the water vapor feedback.
Thanks. I'll just take one more. There's Colin Jones is asking, how important is the efficacy of ocean heat uptake to the overall feedback magnitude?
This is an interesting question for understanding how the feedback, I think for understanding how the feedback changes with time. Here we're estimating these feedbacks after the model sort of has come into equilibrium. So it's not so much about the pattern effect aspect of things. I'm happy to talk about this. This is sort of an involved question. I'm happy to talk about it more offline or later, but basically I think that the efficacy of the ocean heat uptake isn't quite as important to this effect as it would be to, for instance, why feedback changes with time in a transient run. So that's all.
Great, thanks very much, Jonah. There's a couple of other questions in there, but we'll save them for later. So we'll move to the next speaker, please. That's Nick Lutsko of Scripps Institute of Oceanography, and he's going to talk about the relative role of heat versus moisture and heat stress change. You ready, Nick?
Yeah, hello, can you hear me?
Just about, a bit louder.
I'll get closer to the mic, is that better?
That's better, yeah. Thank you.
Okay, yeah. Well, first of all, thanks a lot to the organizers for putting this together. It's a great way to take advantage of the situation. And I also hope that everyone is doing well and staying safe and healthy. I was originally supposed to be in the UK last week and this week. And so I thought that this would be a good opportunity to show some preliminary results on heat stress. And I'm keen to get some feedback and to hear people's thoughts on what I have. I think the motivation for studying heat stress is pretty intuitive. You know, we expect that this could be one of the worst impacts of climate change. particularly for people in the tropics and the subtropics. You know, this could have large impacts on health and mortality and you know, people's abilities to work safely and productively. Can I control the screen? Yeah, okay. But as far as I could tell, it kind of it hadn't really been resolved how temperature versus humidity contribute to heat stress. You know, the body, when it's very warm, we have extra heat input into the body, and the main way that we cool is through evaporation. And so in thinking about heat stress, we have these two components that we have to separate out. So to think about this, the variable that I was using is equivalent potential temperature, theta E. My starting point was just thinking about fractional changes in theta E, which I've written out in the top line here. Can everyone see the mouse? I assume they can. So if you think about fractional changes in theta E, there's going to be one term due to fractional changes in theta and temperature, and then another term due to moisture, due to specific humidity here, the delta QV term. At constant relative humidity, and at least over the ocean, I can use the Clausius-Clapeyron relationship to substitute for delta QV, as I've done here. And then I have a term proportional to QV, a term that's just nothing but constants, and then another term proportional to the fractional change in temperature. If I assume that that fractional change in temperature is the same as the fractional change in potential temperature, i.e. that surface pressure changes are small, then I can have find a threshold value on the baseline QV. Sorry, this L should be an O, shouldn't be there. Above which specific humidity changes will dominate the changes in theta E and heat stress. And this turns out to be a pretty low value of about 5.6 grams per kilo. So in a baseline climate, if there's no change in relative humidity, wherever the specific humidity is above this, specific humidity changes will be the primary driver of changes in theta E. Over land, and if we want to incorporate relative humidity changes, things become a little bit more complicated, but you can proceed through the same kind of derivation to get this criterion on the bottom, where now A is the ratio of warming over land compared to the ratio of warming over ocean. And then I've used some ideas from Robin Chadwick to substitute for delta QV, where we assume that the changes in specific humidity over land, the fractional changes in specific humidity over land and over ocean are the same. So then I have this factor gamma, which is the ratio of the baseline specific humidity over the ocean divided by this baseline specific humidity over land. And I have another term here to account for relative humidity changes. In practice, the threshold specific humidity over land, above which specific humidity changes will dominate heat stress changes, is about 1 to 2 times this QV0 for changes over ocean at fixed relative humidity. So that's a kind of framing of the problem. This is what the changes in theta E look like in CMIP6. So this is a multi-model composite over the 1% CO2 runs. The difference between years 71 to 80 and years 1 to 10 over all the models that had data currently available. So this is a pattern of theta E, and I'm looking at the 98th percentile of theta E, so the change in the 98th percentile of theta E. Panel B is showing the change in potential temperature conditioned on these 98th percentile theta E events. And panel C is showing the change in specific humidity conditioned on these events. And you can see that the map of these extreme theta E events looks a lot more like the map of the changes in specific humidity than the changes in potential temperature. You could almost approximate the changes in potential temperature by a single global mean value. And in fact, if you take pattern correlations of these composites, the R-squared value between panel A and panel C is greater than 0.9, whereas it's only about 0.3 for with panel B with delta theta 98. And this holds just as well in individual models as in the multimodal composite. In panel D, I'm showing the baseline specific humidity conditional on these extreme theta E events, which I'm just taking as the average from years 1 to 10. And this is also fairly well correlated with the change in theta E 98. The R-scored value here is about maybe 0.55, I think. So as a way of checking how this goes against the theory, which was on the first slide, I'm showing here again this panel D, the baseline conditional specific humidity. On the bottom panel, I'm showing the ratio of the changes in specific humidity divided by the changes in theta E. Sorry, in theta, in potential temperature. These magenta lines in the top panel show the 5.6 grams per kilo contour. So basically where it's drier than that, we expect temperature to dominate the theta E changes. And you can see that that works really well in the bottom panel in this ratio over oceans, and that throughout most of the mid-latitudes and tropics, it's really specific humidity which is dominating the changes in heat stress as measured by these extreme theta E events. The exceptions are mostly here in around the Mediterranean basin and intra-Central Asia, and so a little bit over Iberia as well. And to capture that, we just need to increase our baseline threshold to about 8 grams per kilo, though there's some variance in that. So you can't just pick a single number. But so this seems to match very well with this just sort of intuition that we built up from looking at these fractional changes in theta E. There's another way of showing this and focusing in on extreme events now. I'm plotting here the changes in specific humidity versus the changes in potential temperature for all the models that I used in the analysis. And these are changes only for theta E values greater than 305 Kelvin in the baseline climate. So this is only looking how these two quantities vary for extreme heat stress events. And you can see that on almost all the models, the spread in the changes in specific humidity, so the spread along the vertical axis is much larger than the spread in the potential temperature, the spread in the x-axis.
1 minute.
Okay. So this is sort of further confirming this idea that specific humidity is really the key for understanding changes in heat stress. Finally, we can also use this to look at sources of uncertainty, so intermodal spread in theta E. And so what I'm showing here are R-squared values across models for correlations between either potential temperature and these extreme theta E events and specific humidity in these extreme theta E events. So where it's redder, this variable is contributing less to intermodal spread in theta E 98. You can see over oceans, both are contributing quite a lot, and this makes sense. If we think relative humidity changes are small, then it's really temperature that's driving everything, and specific humidity is going to be correlated with that. But over the land, really almost everywhere, it's the specific humidity that's driving the intermodal spread in these changes in heat stress, extreme heat stress events. So again, you know, if we want to understand changes in heat stress and we want to reduce intermodal spread, we really have to focus in on specific humidity. And you know, one basic reason for that is just the rapid scaling of Clausius-Clapeyron. So if you combine that with relative humidity changes, specific humidity could change from, you know, less than 0%, or, you know, it could change by a negative amount or by more than 7% per degree of warming. Whereas temperature is generally going to increase by about 0.3% per degree warming, just, you know, say 1 over 300 Kelvin. And there's not going to be a lot of spread around this. And so we expect much larger fractional changes and a larger range of fractional changes in specific humidity than of temperature. And so it's only in the coldest, driest climates that temperature is going to be the driver of theta E changes. But for regions that are in danger of having strong changes in heat stress, it's really the specific humidity that's going to be driving everything. Okay, thank you.
Thanks so much, Nick. I don't think there's any questions in the forum at the moment, actually. Oh, there is one, actually. Colin Jones wants to ask if there's a diurnal cycle to the specific humidity changes. How important are nocturnal changes in heat stress?
Oh, that's a great question. I hadn't thought about that. This is looking at daily data, I should have said. So I don't think that resolves daily mean data. So that doesn't resolve the diurnal cycle. That's definitely an interesting question.
Okay. Thank you very much again, Nick. If we just move to the final speaker now, it's B. Predoi from NCAS, Reading. And he's going to talk to us about ESMValTool, which some of you are probably very familiar with as a way of analyzing CMIP6 data. You ready, V?
Yes, sir.
Take it away.
How you guys doing? Thanks for the introduction, Andy. I'm gonna ask Hazel to move to the next slide so that we get to the meat of it. So, few words about ESMValTool, which is a diagnostics and metrics package that compares your favorite CMIP models with other CMIP models, or models with observational data, or even CMIP models with different versions. So if you want to get these comparisons done, what you do is you use the ESMValTool that actually uses scientific diagnostics, peer-reviewed and published diagnostics. So from a technical point of view, ESMValTool is a mostly Python package, and I'll tell you why is it mostly Python package. It relies on reproducibility, so it's got a powerful provenance module so that you can actually track the diagnostics and how they change over time, and track the results. It is hosted on GitHub. The source code is hosted on GitHub, where all the development work is being done. There you also have a continuous integration machine that assures that any change in the code is reliable and it doesn't change previous behaviors. It is deployed on Conda, on Anaconda, so that installation can be done via a Conda environment that you build, and we're planning on deploying it to the Python package index, the PyP. From the support point of view, obviously it's open source, fully open source. You come over there and you ask your question, or you open an issue and you ask for your favorite diagnostic to be implemented, and offer yourself as volunteer to do that, and then you can actually browse all the other issues and the problems that have been addressed in the past. In terms of the structure, the code structure, it is divided into two operational packages, sub-packages. It's one that is pure Python, the preprocessor, or as we call it, ESMVal core. This is the sub-package that does all the heavy-duty computations, for instance, regrading, multimodal analysis, statistics, masking, all the toolboxes that the analysis, the diagnostic needs to run. This is done in the preprocessor, and it's good because it's a standardized set of modules that can be used, can be called and used at any time, lightening up the diagnostic itself. So the diagnostic can actually concentrate on the science rather than be concerned with a whole bunch of standardized analysis. And the diagnostics, obviously the ones that are developed by the scientific community, and there's a very large support from among the community, as we have some 40 institutions that collaborate and develop diagnostics and contribute to the diagnostic pool. And there's a bunch of, basically supporting anything from CMIP3, so CMIP3, 5, 6, Cordex data and observational, all sorts of flavors of observational data and anaphromIPs and OSPROMIPs and so on. So it's got a pretty wide data coverage and institutional collaborators coverage. We obviously need you to come over and be one of the developers, because this is how the tool grows, by contributing and writing your diagnostic and contributing to the pool of diagnostics in ESMValTool. From a technical point of view, diagnostics can be in different, they're written in different languages, Python, NCL, R, and even Julia. So we're trying to support as much as possible, because we are aware that some scientists are more proficient in one language as compared to others. So, but these are the main ones. And we're not extending the supported languages. Can we go to the next slide, please? So there's a whole bunch of output results here. I am a software engineer, so I can't really tell you what those things are, but you're a scientist, so you figure out. There's a bunch of stuff. It's the bottom left one is actually the perf-metrics, what we call the perf-metrics plot. Is basically throwing in all the possible and impossible CMIP models into one big diagnostic, and throwing in a whole bunch of observational data sets there, so we can actually see the behavior of the tool. So it's kind of like a calibration of the tool. I would recommend you guys go to the website. Actually, if you go to the next slide, you'll see the can we go? There we go. Thank you. And that's the last slide. So the website lists the ESMValTool.org. It lists all the possible diagnostics via a very nice gallery. So you can actually see what the output of the diagnostic is via images, and then you can click on it. It'll take you to the particular diagnostic documentation. So in terms of the support that we're offering well, that's the anything via GitHub. So if you go to GitHub, there's the possibility for you to open the issue and talk to us directly through the GitHub interface. And then we offer a range of tutorials and online workshops. Well, we're restricted to online now, but hopefully in the future we'll be able to come back to actually offer you the actual workshop. And we are providing a couple of mailing lists as well, so people can just shoot an email and ask the question. And yeah, I mean, that's pretty much it. I like to take questions, and I like people to be if you're interested, come back to us in any form, any contact form possible.
Great. Thank you very much, Lee. We've got one question so far. Jeremy Walton's asking if there's a favored language you prefer new diagnostics to be written in.
No, there is no favorite language. We're trying to steer people to write their diagnostics in whatever they feel more comfortable. Preferably not in NCL. No, that's a bit of a joke. NCL is actually going to be, well, it's not going to be supported anymore. So if you write diagnostic in NCL, then it's fine. But in X amount of time, in a few years' time, NCL will lose the support. So they will actually migrate to Python. But whether it be Python or NCL or R or Julia, that's fine. It's all up to you.
Okay. Another question from Colin Jones, asking if you have an update on the planned online tutorial that's intended to coincide with the CMIP6 workshop. I think this workshop, actually.
Yes, I would actually, I would ask Ranjini if she wants to comment on this, because Ranjini is our main person with respect to tutorials.
Yes. Hi, Colin. Yes. We are doing a trial run of the virtual tutorial, and we're going to shortly be able to conduct one as planned for the people who signed up as part of the CMIP6 workshop. The trial tutorial we're going to see, the virtual tutorial, the first one that we're going to run is going to be this week. So yeah, we'll have an update early next week.
Great. We haven't got any more questions, but just one comment from Brian Lawrence, just reminding us that NCL has migrated to a community package rather than an NCAR package, so it's not disappearing just yet. And I think Colin has just asked, I think it's in the context of what you were just saying, Ranjini, about a timescale.
I guess we could send out a doodle poll or something early next week to see when people will be available. Does that answer your question? But if this Friday's tutorial goes successfully, then we're ready anytime after that, based on availability of people.
Okay.
Okay, this is Colin here. I seem to be able to unmute myself. Yeah, I think it does, Ranjini. I guess all I'm getting at is now that we've got people involved in these online things, to keep the momentum, it would be good to give them an indication that there will be an online tutorial coming.
Yes.
Okay,
great.
Thanks.
Well, I think that we're almost out of time. So I'd like to just thank our speakers for the talks just now. And thanks for everyone for attending. As I mentioned at the start, the intention is to try to do this again sometime in May. And the date for that is just being worked out at the moment. So we'll be all back in contact with you about that down the line. Thanks again, and hope to see you all again before too long. Stay safe, everyone.